So today we are going to begin the fourth chapter for this course, and it is on probability. This is also the fourth week or fourth module for the course. What we're going to do is we are going to build the fundamental idea on probability today so that we can go into more detail of this chapter in next class. First, we are going to begin with some fundamental terms required in this topic, probability. Remember, probability is a big content for this course, and we need to know every little detail of this chapter. First, we are going to talk about something called an experiment. So when we say an experiment, it is a planned operation carried out under controlled condition. That is, when you perform the experiment, if the result is not predetermined, or we don't know the result of the experiment, then we say that the experiment is said to be a chance experiment, or we say random experiment. Here I have three examples of the experiment. The first one is flipping a fair coin twice. You have a coin and you're tossing the coin. You don't know the outcome, what you will get, whether you will get head or tail, you don't know. That is an experiment. Or rolling a six-sided dice is an experiment. When you roll a dice, you don't know what is your outcome. You may get 1 or 2 or 3 or 4 or 5 or 6. Or if there is a spinner, you are spinning a six-colored spinner, we don't know the outcome, where it will land. So that is also an experiment. I'm going to show each of these. These are the link in your note catcher. If you click this, it will take you to the animation. So I'm going to show you that animation. First, what I'm going to do is I'm going to stop sharing this screen and share the second screen where I can show you the animation. So here I have the first one. You can see here flipping a coin. If we flip a coin, what is the outcome of this experiment? We don't know. Let's flip it and check. So we are going to flip it 2 times here. So if I flip it once, you can see the first time I get the head. You can see in the coin. I mean, first time I got the tail. Do you see that? I got a tail here and the graph is shown there, 100% tail. Now, if you flip it again 2 times, flip it again, you can see the second time also I got the tail, same thing. If I flip it again, let's see, let's do it a few more times. If I flip it again, I'm getting tail. Flip it again, I got head. So remember, when you perform the experiment in real life, it's not that you get first head and then tail, head and then tail. It's not going to happen something like that. Here I performed the experiment 4 times and I got head 3 times. 75% of the time I have the tail, 25% of the time I have the head. If I flip it again, you can see I again got the tail. Tail 80% of the time, head 20% of the time. If I flip it again, you can see I got head this time, so that the percentage is changing. Head 2 times, tail 4 times out of 6. So this is the experiment, the random performance of anything, that is the experiment. And in the experiment, you don't know the outcome. The second example was rolling a dice. Here is the dice you can see here. We don't know the outcome. When you roll, you may get 1 or 2 or 3 or 4 or 5 or 6, but we don't know what we will get. Let's roll it. For the first time, I got a 5. So 100% of the time I have 5. 5 one time. Roll it again. I did 2 times. The second time I got 3. So 3 one time, 5 one time. So 50% each. Roll one more time. Again, I got 5. So 5 I got 2 times. 3 I got 1 time. Roll it again. See, I'm performing the experiment. I again get that 5. Roll it again. Again 5. Roll it again. 6. So you can see the outcome of this experiment is listed here in the frequency table. For example, the values I'm getting, I got 3 one time, 5 4 times, 6 one time. Roll it one more time. Let's see what you'll get. I got a 1. So 1 one time, 3 one time, 5 4 times, 6 one time. So that's the experiment. I don't know the outcome, but I am repeating this act and I'm getting the result. Okay, let's do one more. That was spinning the colored spinner here. So if we spin this, let's see what we get in the first trial. If I spin this in the first trial, let's see where I land. I land in this purple color or the violet color. Spin again. This time I'm landing on blue color. Spin again. I am landing on red color. So that is the experiment. Let me stop sharing this and go back to the previous one. Okay, any question on the experiment?
No.
Okay, so remember experiment, when we perform the experiment, we don't know the outcome, okay? We actually do the experiment and we record those outcomes. So now you know what is outcome. When I say outcome, that is the result of the experiment. The result of an experiment is outcome. For the following experiment, let's see, here we have the same experiment that we have seen before, flipping a coin twice. If you flip coin twice, what you will get? Let's think of that. If you flip the coin, then you may get head first. Let me write that. You may get head first and again head. Is that possible? First you get a head and also head, right? That's possible.
Yes.
First you get a
Mm-hmm.
head, then you get a tail. That's also possible. First time you get head, second time you get a tail. Or first time you get a tail, then second time you get a head. Or first time you get a tail and second time also you get a tail. Right? These are the outcomes. Are there any other outcomes when you flip a coin twice? Think of
No.
that. No, because these are the only possibilities. We can also represent this using a tree diagram. For example, we can do this. So in the first, when you roll or when you flip the first coin, you may get head or tail. That's how we write. And then once you have the first outcome is head, then what will be the second? Second time you may get head or tail. Okay? Or say, for example, first time you get a tail and you're tossing the coin second time. You may again get a head or a tail. So if you want to list the outcome here, see the outcome will be first head and second head. So head, head. That's what I have written here. First can be head and the second is tail. So head, tail. The second outcome will be head, tail. That's what I wrote here. The next outcome here, the first tail and then head. First tail and then head. So you can write tail, head. And the other possibility is tail and then tail. Tail and then tail, which I wrote here. So I list these four possible outcomes. So here I have these outcomes. So when you flip a fair coin, these are the possibilities. These are all possible outcomes. These are all possible outcomes. These are all possible outcomes. When you flip a coin twice, always remember, you must know this one, how to write all possible outcomes. That is very, very important. You can use the tree diagram or you can perform the actual experiment. Let's look at this one. Rolling a six-sided fair dice. When you roll a dice, what do you get? What are the possible outcomes? You may get a 1 or 2 or 3 or 4 or 5 or 6. So these are all possible outcomes. All possible outcomes. You can also write this in your note catcher. All possible outcomes. And the last one is spinning a 6-color spinner. What were the colors? Can you remember those colors? Do you know what were there? No idea? We'll go back and check it.
Violet.
So the colors were violet, orange, blue, red, yellow, and green. So these are all possible outcomes. All possible outcomes. So the outcomes are nothing but the result of the experiment. And there is a special name for this set of all possible outcomes. And the set of all possible outcomes, they are called the sample space. Okay, the set of all possible outcomes, they are called the sample space. The sample space of an experiment is the set of all possible outcomes. There are several ways to find or represent the sample space. It can be by listing. When I say listing, listing is like this. For this one, I listed as head, 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 tail, tail, head, tail, tail. That is listing. Okay, or you can also create a tree diagram, or we can also create a Venn diagram. You have already seen how to create a tree diagram. Creating a Venn diagram for some problem, you'll see that later on. This one, what is the sample space for rolling a six-sided die? You have seen it is 1, 2, 3, 4, 5, 6. I'm writing all possible outcome. That is the sample space. And we write sample space like this. This is equal to set S. This is equal to set S, sample space. We can write equal to S, or first you can write S equal to and then list the elements in that space. So what were the different color? Help me recall those colors again.
Violet,
Violet, then?
Blue,
orange, blue,
Okay. Violet, orange, blue, then?
red,
Red, then?
yellow,
Yellow,
and green.
and green. Very good. So these are all possible outcomes. So always remember the set of all possible outcomes, that is called the sample space. So we look at three main definition here. If we go back and check it, see the first one is experiment. Okay, in experiment, we normally don't know the result of the experiment. The result of the experiment is generally predetermined, is not predetermined. Second, we talk about the outcome. The result of the experiment is the outcome. And here we listed all possible outcomes. And this set where we list all possible outcome, that is called the sample space. And we denote this set using the uppercase letter S. This is the set. That is why these outcomes are enclosed within this bracket. You can see I'm using this bracket. Okay, a curly bracket. I call it curly bracket. These are the set bracket. So make sure you use the proper notation. You must use the curly bracket for the sample space. Always remember, you cannot use parenthesis there. Okay, now here is the example where you are asked to write the sample space. Look at this example. A survey consists of asking people for their blood types. When we say blood types, there are 4 different types of blood: O, A, B, and AB. And these are further classified depending on the type of RH present in the blood. So including whether they are RH positive or RH negative. Meaning of that is, when you have blood type O, you may be O positive or O negative. When you have A, you may be A positive or A negative, depending on what type of RH factor is present in your blood. So if that is the case, what we are asked to do is, we are asked to determine the number of outcomes, how many outcomes are possible, and then we are asked to write the sample space. So let's try this one. I'm going to use a tree diagram to solve this. So what I'm going to do is, first, I'm going to list 4 different types of blood. You can also follow along with me. O, A, B, and AB. These are the 4 different types of blood. Now, when someone has blood type O, they may be O positive or O negative. When someone has blood type A, they may be A positive or A negative. If someone has blood type B, then they may be B positive or B negative. And if someone has blood type AB, then they can be AB positive or AB negative. So now if you look at the outcome, so I draw the tree diagram. If you look at the outcome here, the first one is O positive, second is O negative, the other one is A positive, next is A negative, then you have B positive, then you have B negative, then you have AB positive, and the last one is AB negative. So we draw the tree diagram. Now let's answer the question. Determine the number of outcomes. So the first answer, we are looking at number of outcomes. Number of outcomes is equal to, you can count here, how many are there? 1, 2, 3, 4, 5, 6, 7, 8. Number of outcomes is equal to 8. Then we are asked to identify the sample space. That means we need to write that sample space. Sample space is the set S where we list all possible outcomes. So we write all these outcomes in the set. So that will be O positive, O negative, A positive, A negative, B positive, B negative, AB positive, and AB negative. So that is your sample space. Do you have any question on how we get the sample space?
No.
Just say yes or no.
No.
Can you
Okay.
hold on for a second?
You have a question?
Oh, no.
No. Okay.
No, thank
No problem. Let's go. Next one. Okay. Here, we are asked to construct a sample space for rolling 2 dice. Okay, here we are rolling 2 dice. If you roll 1, the possible outcomes are 1, 2, 3, 4, 5, 6. So if you roll 1, the possible outcomes are 1, 2, 3, 4, 5, and 6. And if you roll the same outcome, you'll get 1, 2, 3, 4, 5, or 6. But what happens if you roll 2 dice simultaneously? If you roll 2 of them at the same time, what are the possible outcomes? So we are going to list all those outcomes here in the form of a table because we are getting so many outcomes there. You'll see that in a second here. So the possibilities are, say for example, you'll get 1 on the first and 1 on the second. That's possible. You may get 1 on the first and 1 on the second. You may get 1 on the first and 2 on the second. 1 on the first, 2 on the second. The other possibility is 1 on the first, 3 on the second, 1 comma 3. 1 on the first, 4 on the second, that will be 1, 4. 1 on the first, 5 on the second, 1, 5. 1 on the first, 6 on the second. 1 on the first, 6 on the second. Look like my computer is frozen. Oh, it's there. So do you have any question on the first line, how I got those values? 1 on the first, 1 on the second, 1, 1. 1 on the first, 2 on the second, 1, 2. 1 on the first, 3 on the second, 1, 3. 1 on the first, 4 on the second, 1, 4. 1 on the first, 5 on the second, 1, 5. 1 on the first, 6 on the second, 1, 6. Right? Is there any question on the first line? I want some of you to unmute yourself.
No.
No.
Okay. Okay, now let's continue the same way, like 2, 1, 2, 2, 2, 3, 2, 4. Let's complete that table. 2, 1, this is 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3 on the first, 5 on the second, 3 on the first, 6 on the second. 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. Then we have 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6. And the last one, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. So you can see here we have total of 36 possibilities because you have 6 on the first and 6 on the second. 6 times 6, 36. So this is the sample space. Everything written in red here, these are the elements of the sample space. So you can see you have in the first 6 possibilities, in the second 6 possibilities, 6 times 6, the total will be 36. If you go back and look at the previous example, you can see there are 4 blood types and there are 2 RH factor. So 4 times 2, the total possibility is 8. That's how we got. Total outcomes is 8 because it is 4 times 2. RH factor 2 type. Similarly here, you have 6 possibility on the first eye and the 6 possibility on the second. So 6 times 6, 36. So in these 2 examples, we learned how to write the sample space. We are building the fundamental idea required for the calculation of probability. Okay, any question up to this point?
No.
Okay,
When
great.
you get that 6, is that because of the dice have
6-sided, yes.
Okay.
That's right. Because there are 6 possibilities on the dice, 1, 2, 3, 4, 5, 6. So that's why I got those numbers. Other questions before I move on? Okay, look like there is no question. Now we are getting into the definition of probability, how we can calculate the probability. And the first one we are talking about is the classical or theoretical probability. What is classical or theoretical probability? Let's go and study this one. Let's look at the definition. In classical or theoretical probability, each outcome in a sample space is equally likely. So meaning of that is, if you remember the first animation we did, we toss a coin. When you toss a coin, what we think is, we think that we get head and tail equally. For example, if I perform the experiment 10 times, then what I think is I may get head 5 times and tail 5 times. That is the consideration in the classical probability. It considers that the events are equally likely. An event is the combination of outcome. When I say event here, like if I perform the experiment 3 times, in 3 times, what are the outcomes? That is the event. So based on that, this is how we define the probability. Probability of any event E, which is written as PE, probability of any event E is equal to number of outcomes in E, okay, or number of favorable outcomes, we also say that. So how many are there in E and how many outcomes are in all? So it's the number of outcomes in E or the event divided by total number of outcome in the sample space. In simple way, we write like this: probability of any event E equal to number of element in event E divided by number of element in the sample space. So you can copy that formula. We'll be using that formula. Probability of event E equal to number of element in the event divided by number of element in the sample space. And when you compute the probability, remember, this is very important. When you compute this probability, when you find the value of the probability, your value of probability can be 0 sometimes, or sometimes it can be 1. But most of the time, the value of the probability is a number between 0 and 1. So probability is not less than 0. Your probability cannot be 0. Very important to note that. And the value of probability cannot be more than 1. So when you're computing the probability, remember that it cannot be more than 1 or it cannot be less than 0. If you get anything more than 1, tell yourself you did something wrong. If you get anything less than 0, then also you are doing something wrong. Probability is always between 0 and 1. Now it has a meaning. If the probability is 0, meaning of that is the event is not going to happen. For example, what is the probability that my age will be 2 years again? That's impossible, 0. Okay? Or when we have probability 1, in that case, we say that the event is going to end, or event is going to happen anyways. So that is the certain event. What is the probability that we are going to end this live session soon? The probability is 1. We are going to do that. Definitely we are going to do that. Okay, so that is the certain event. If the probability is 0.5, 50%, meaning of that is the probability that event is going to happen is equally likely. It can happen or it cannot happen. That is the meaning. If your probability is more towards 0, like 0.25, we say that the event is unlikely. You are looking at your weather app and it has shown that the probability that it will rain today is about 25%, 0.25. Meaning of that is it is unlikely that it will rain. But if you see that the weather app is showing that it's going to rain and the probability is 75% or more, then it is likely it's going to rain. So that is the fundamental idea or definition of probability. And this definition of probability is the classical definition of probability. Okay, any question on that? Yes, no?
No.
Okay, great.
Nope.
Okay, if you have no question, we'll go to next slide and find out what is there. Okay, look at that. So you can see there are cards because you like cards. Do you play cards? Now it's time to talk. We can talk now.
Sometimes.
Sometimes,
Yeah,
okay,
sometimes.
that's good. Classical probability, we have this formula. Probability of any event E is equal to number of element in the event divided by number of element in the sample space. Before we read the question, let's talk a little bit about these cards. So in a standard deck, how many cards are there in all? Who can tell me?
52.
52. 52 cards are there. Also, we have 10 minutes before this session end. If the session end, we'll come back 10 minutes after that, okay? So here you can see I have the standard deck. There are 52 cards, and you can see on the first row here, what type of card is there? There are 4 different types. What type of card is this one? What is this called?
Clubs.
Club. In the second, you'll see the second type of card. What is it called?
Spades.
Spade. In the third, you'll see the third type of card. What is it called?
Hearts.
Heart. And the last one, you'll see the other type of card. What is it called?
Diamonds.
Diamond. Make sure you know the name because that is required. And in each type, there are 13 cards. Here we have 13 cards. Here we have 13 cards, 13 cards, 13 cards. Okay. And you can see because we have 13 and 13, there are 26 black cards and 26 red cards. Always we start with the A or ace. Then we go to 2, 3, 4, 5, 6, 7, 8, 9, 10. Then jack, queen, and king. Everything from A up to 10, you don't have a picture of anyone on that, just the symbol for the card. But after this, you'll see the face on the card. Face on the card. So these cards, these 3 cards here, they are called the face cards. Okay? Face cards are there. Red cards are there. Black cards are there. There is a club, spade, heart, and diamond. So after we have this fundamental idea, let's work on the problem. Let's see what is given here. A card is drawn from ordinary deck. Calculate the probability of getting a club. Okay, what is the probability of getting a club? We need to find that. Probability of getting a club is equal to, you can see the way we calculate the classical probability is number of event. So in this case, number of club divided by total. How many club are here? You can see here. How many club are there? 13, right? Each type of card, that's 13. So you have 13 out of 52. 13 over 52. Or when you reduce this, it is 1/4. You can leave that as 1/4, or you can change it to decimal. So when you change it to decimal, you'll see that this is 0.25. I told you probability is a number between 0 and 1, and we got that. Next, we have to find the probability that it's a red card. Probability that it's a red card. How many cards are red? Here we have 13. Here we have 13. 13 plus 13, 26 out of 52. 26 out of 52 is same as 1/2 or 0.5. Again, you can see the probability is between 0 and 1. Now this one, third one. What is the probability that the card is 7 of heart? Probability that it is 7 of heart.
1/52.
That's right. There is only 1 7 of heart, right? In heart, there is in heart here, There's only one 7. So 1 out of 52. 1 divided by 52. You can leave it like that or change it to decimal and you'll get the value 0.0192. Next, we have to find the probability that it's a king. Probability that it's a king. How many kings are here? You can see 1, 2, 3, 4 kings. 4 out of 52, which is 1 divided by 13. You can leave it like that. Or when you change it to decimal, that should be 0.0769. And the last one, face card. How many face cards are there?
9.
Face cards, 9 or 12? 3, 1, 3, 3, 2, 6,
12.
2, 3, 9, 3, but 12, right? 12 divided by 52, which is equal to 3 over 13, right? When you reduce that, 3 over 13, which is same as 0.2308. Okay. So that is the end of this example. I'm also going to end the recording right here because we are about to end with the session.